Hello class, today I'm going to discuss the pre-lab experiment for molecular geometry. So the learning outcome for this experiment 4, you should be able to draw the Lewis structure of a molecule or polyatomic ions, apply the VSEPR theory to determine the molecular shape, and also draw the basic molecular geometry of the molecule and polyatomic ions. Okay, so the introduction. Okay, so to do this molecular geometry, first we must draw a correct Lewis structure in 3D dimension, and then afterwards, based on the electron group arrangement, okay, we are going to determine the geometry of a molecule. So the geometry of the molecule is based on the VSEPR theory, which is known as valence shell electron pair repulsion. So in the VSEPR theory, the repulsion between the two pairs of electrons in the shell, okay, will determine the geometry of a molecule. So based on the VSEPR theory, we will try to arrange the bonding pair of electrons, okay, as far as possible in order to reduce the repulsion. So here I'm going to guide you step by step on how to draw the Lewis structure. So step 1, we're going to sum the number of valence electrons for all the atoms. And step 2, draw the skeletal structure of the molecule by using the less electronegative atom as a central atom, and the more electronegative atom is the terminal atom. So means that we're going to choose a less electronegative atom or the most electropositive atom at the center. And step 3, we're going to distribute the remaining electron to fill the octet of the terminal atoms. So it means that we're going to fill all the terminal atoms and make them octet, which means that all of them will have 8 valence electrons. So the VSEPR stands for valence shell electron pair repulsion. So these are the general formula. Okay, so based on the general formula, X1A stands for our central atom and X is our terminal atom. So it means that there's one central atom and 2 terminal atoms. So this is a molecular geometry. So the predicted geometry is linear and we will have 180 degrees angle. So for example, of the X2 is carbon dioxide. And then at X3, so when there is one central atom and 3 terminal atoms, so based on the VSEPR theory, the best arrangement will be in trigonal planar. So each of the angle between the bonding pair will be 120, 120, and 120. For example, boron, fluoride. And Exp4, the predicted arrangement will be tetrahedral. So we have one center and 4 terminal atoms. So the angle between all the bonding pair will be 109.5 degrees, and the example will be tetrafluorocarbon. And X5, the predicted geometry where the repulsion will be least is in trigonal bipyramidal shape. So trigonal bipyramidal, so there will be 2 angles. So between the triangle, okay, between the triangle which you can see, this is a triangle. Okay, there's a triangle. Okay, so it's a planar. Okay, so there's a triangle. So between these 3 bonding pair, the angle is 120, and between the top and this angle, okay, is 90 degrees. And the last one, when there is one central atom and 6 terminal, we will be arranged in the octahedral geometry, which you will have all the angle are 90 degrees. So how you arrange? Okay, so here we have a square plug. Okay, so on top of the square, we will have one bonding pair on the top and another bonding pair at the bottom. Okay, so before we do the molecular geometry, you need to learn how to draw your Lewis structure. So let's look at the example, the beryllium chloride. So beryllium chloride, Be, there are 2 valence electrons in Ve, and then for chlorine, there are 7 valence electrons. So 2 chlorine, so the total of valence electron is 14. So step 1, we sum up the valence electron for Be and Cl, which is the total will be equal to 16 electrons. And step 2, we're going to draw the skeletal structure. So when you draw the skeletal structure, you have to put the least electronegative atom at the center. So the least electronegative atom here is beryllium, Be. So our skeletal structure will be Be in the center and Cl as the terminal atom. So the skeletal structure, okay, I need to use 4 electrons. Okay, so 2 electrons will be used to draw a single bond, and another 2 electrons will be used to draw another single bond. So this is a skeletal structure. So it means that 4 electrons has been used to draw the skeletal structure. So after minus 4 electrons, so I will left 12 electrons. So step 3, we're going to distribute the 12 remaining electrons, okay, to fill the octet of the 2 chloride atoms. So it means that we have to distribute the 12 electrons on the terminal atoms so they can become octet. So 6 electrons will be put at one chlorine atom, and another 6 electrons will be put at another chlorine atom. So there's no more electron left. So you can see the chlorine atoms, they has 6 surrounding electrons, and then you have 2 share electron with your beryllium. So the chlorine atoms have achieved octet configuration. But for Be we have 4 share electron, okay, with the chlorine, have 4 share electron with the chlorine atoms, so it is incomplete. But you have to remember that for beryllium, it can exist as stable incomplete octet. So it means like for beryllium, it will be stable although it is incomplete. So there are 4 atoms, there are 3 atoms which can exist in the incomplete octet, which is your beryllium, boron, and your aluminium. So we will look at more examples after this. So this is a complete Lewis structure for beryllium chloride. So now let's look at another example, AlCl3 aluminium chloride. So the step is similar to previous example, which is first we have to sum up the valence electron for aluminium and chlorine atom. So aluminium has 3 valence electrons, and for chlorine atoms, okay, one chlorine has 7 valence electron, and there are 7 chlorine in the molecule. So 3 multiplied by 7 valence electron. So the total number of valence electron is 24. And then on step 2, we are going to draw the skeletal structure. So aluminium is least electronegative, so it will be at the central, and chlorine atom is more electronegative, so it will be the terminal atom. So our skeletal structure, Al center, and then you have Cl at the side. So to draw the skeletal, okay, you need 6 electrons, which the 6 electrons, so 2 electrons, okay, will be used to draw a single bond. Okay, so total 6 electron will be used to be used as the single bonding. So after use 6 electron, okay, we have 18 electrons left. So what's going to happen is the 18 electrons, we are going to distribute them to the terminal atoms, so we can make the terminal atoms octet. Octet means that you want to make them has 8 valence electron, which is more stable. So we're going to fill all the terminal atoms. Okay, so the first chlorine atom I fill with 6 electron, and it has 2 shared electron with Al. So now the chlorine atom have achieved the octet configuration. So same with another chlorine atoms and another chlorine atoms. So now all the chlorine atoms, okay, I've used 16 electrons to fill the 3 chlorine terminal atoms, and there's no more electron left. So you can see my Al, okay, for my aluminium atoms, there are 3 bonding pair with chlorine atoms. So it means that Al only had 6 electrons. Okay, there's only 6 electrons surrounded my Al, which is incomplete. Okay, so my Al, okay, can exist in the stable incomplete octet. Okay, so means that this restructure is complete. So you have to remember, normally for all the atoms, we have to make them octet, which means that they need to have 8 surrounding electrons, except there are 3 atoms which has the special case. So the atom is Be, B, and Al. So these 3 atoms, okay, they are stable as a incomplete octet. So next example will be tetrachloromethane, or also known as carbon tetrachloride. So we calculate the sum of valence electron for carbon and for chlorine atom. So one carbon have 4 valence electrons and 4 chlorine atoms. Okay, so 4 multiplied by 7, you will get 28 electrons. So the sum of the valence electron is 32. So step number 2, we're going to draw the skeletal structure. So carbon is least electronegative. So carbon will be in the center, and Cl is more electronegative, so it will be at the terminal. So after you draw the skeleton, okay, we're going to use 2 electrons for 1 single bond. So here we will have 4 single bond which connect your central atom and your terminal atom. So 4 single bond is used to draw the skeletal structure. So it means that we have used 8 electrons, okay, to draw the skeletal structure. So there will be 24 electrons left. So the step number 3, we're going to fill all the terminal atoms with electron so they can be octet. So 24 electrons, okay, I'm going to fill one chlorine atom with 6 electrons. So the chlorine atom will achieve stable octet configuration, and then another one with 6 electrons, another chlorine atoms with 6 electrons. So all the chlorine atoms are filled with 6 electrons, and they have 2 shared electrons with the carbon atom. So it means that all the chlorine atom has 6 surrounding electrons. So they have achieved octet configuration. And how about my carbon? So carbon have 4 single bond. So it also has, so 1 single bond is made of 2 electrons. So it means that my carbon has 8 shared electrons okay, with the chlorine. So my carbon has also achieved stable octet configuration where there are 8, okay, surrounding electrons around my carbon. So when all the atoms such as your carbon and chlorine has achieved the octet configuration, so means that our Lewis structure is complete. Okay, so remember, normally all the atoms, including the central and also terminal atoms, need to achieve octet configuration for the Lewis structure to be complete. So except the 3 special atoms, which is your B, Be, B, and Al. So they can exist as incomplete octet. Okay, so now let's try another example, BCl5, which is phosphorus pentachorite. So phosphorus is in group 5, so it will have 5 valence electrons, and chlorine group 17, so it has 7 valence electrons. So 5 electron from phosphorus, and there are 5 chlorine atoms, so 5 times 7 you will have 35 valence electron. So the sum of the valence electron is equal to 40. And step 2, we're going to draw the skeletal structure. So phosphorus is least electronegative, so it's going to be in the center, and chlorine is the terminal atoms. And okay, so in this skeletal structure, okay, we have 5 single bonds which used to connect the central atom and the chlorine terminal atoms. So there are 5 single bonds, so each single bond is made of 2 electrons, so it means that we have used 10 electrons in drawing the skeletal structure. So 40 minus 10, we left 30 electrons. Okay, and then the step number 3 is we're going to make the terminal atoms octet. So the 30 electron will distribute among the terminal atoms. So I'm going to put 6 electrons each on the chlorine atom. Okay, so all the remaining 30 electrons are filled on my terminal atoms. So there's no more electron left. So now let's check. Each of them has achieved octet configuration. So all my chlorine atoms, okay, all of them have 8 valence electron. So chlorine atoms have achieved stable octet configuration. And for my phosphorus, the central atom, so my phosphorus has 5 single bond. So it means that there are 10 electrons around my phosphorus central atom. So normally all the atoms will stable as octet configuration, which is 8 valence electron. But for atom which is on the group 3 and above, okay, so if the atom is from period 3, okay, if a central atom, sorry, is from period 3, okay, not group 3. So if a center atom is on period 3 and above, okay, it can has more than 8 valence electrons. Okay, so for example, my phosphorus, it has 10 electrons surrounded. So this one we call it expanded octet. Okay, so P is stable in the expanded octet configuration. So this is my complete Lewis structure. Okay, so after you draw all the Lewis structure for the following molecules, okay, so based on the Lewis structure, we are going to apply the VSEPR theory and predict what is the molecular geometry. So there are 5 basic molecular geometry, which is linear, trigonal planar, tetrahedral, trigonal, bipyramidal, and also octahedral. So how can we predict the molecular geometry? You can refer to this table to predict the molecular geometry, which is when the molecule has 1 central atom and 2 terminal atoms. So such as your beryllium chloride. So beryllium chloride one beryllium central atom and two chloride terminal atoms. So the best molecular geometry where repulsion can be reduced is you arrange in linear. So so the bonding pair is far apart, and the angle between in this linear geometry where will give the angle of 180. And X3, so just now the example which we use is aluminium chloride. So aluminium chloride, you will have the predicted geometry of trigonal planar, and the angle is 120. So you can go to this table to complete your basic structure and the bond angle for the following molecule. So for beryllium chloride, beryllium chloride, the molecular geometry is linear, so the angle is 180, and general formula is X2. And aluminium chloride is trigonal planar, and bond angle is 120, and general formula X3. And tetrachloromethane, so the angle is 109.5 degrees. So this is a structure of tetrahedral. General formula is X3. And for phosphorus pentachorite, so we will have a trigonal bipyramidal. So trigonal bipyramidal means that you have a triangle plane, triangle plane here, and you have a top which it will look like a pyramid. So how the structure like is you have a triangle plane, and then you have a bond on top here, so it look like a pyramid. And another bottom, you have another bonding pair. So it look like two pyramids, so we call it trigonal bipyramidal. So the angle between the triangle, between this triangle here is 120, and between the top and the bottom, the angle is 90 degrees Celsius. Oh, sorry, it's 90 degree. It's 90 degree. I hope this video helped you to prepare for pre-lab experiment 4. Please like, share and subscribe if you like my videos. Thank you.